So hello, everyone. As she just said, I'll be talking about LLM, AI agents, and RAG. So following up from a few talks that we had here about this. But first, let me introduce a little bit more about myself. I live in the Netherlands now, but I was born in Brazil, have been working there for 20 years, and maybe too close there. I'll try to come here. So I work mostly with Java. So I have been working with Java for a long time, for these 20 years, most of it. And during my spare time, I usually like to play or watch soccer, football, and have barbecues over the weekend. But at some point, like 8 years ago, I was presenting a research paper at the Fields Institute, and I really like the environment with different people, different cultures. This is something that we don't have much in Brazil, so because of the language barrier. And I decided that it was a time for a change. And that's when I came to the Netherlands. And there I have been working for different companies. I went there to work for Adyen, the payment provider that supports Facebook, Uber, and many other big techs. Later, I switched to book.com, where I still work there. And I'm starting also my own consulting based on AI technologies. And I'll share a little bit of this experience with you today. But first, let's try to start with a demonstration. I wrote a simple demo for you. This is the architecture of the example. A user input will go to the application that will handle natural language processing and text-to-SQL. This will go to the database and will produce a natural language response for the user. So it's not exactly like a chatbot, it's more oriented. It looks more like specialist systems that we have been creating for a long time. This is also a database that I created for this example. So this is a logistics order tracking database. We have orders, shipments, tracking events. So basically anything that you need to have a very simple thing like Amazon and store orders and track the systems. Let's check the demo then. So let me see if it's still running. All right, that's good. So this is the input. The result here will be the actual query instead of the natural language response that I mentioned before. This is just to demonstrate what is being generated on the back end. So if a user go to this system and what's the status of my latest order, the system would produce these queries. It looks okay. It's going to the orders database. It's going also to the shipments database and getting the status for there. So that looks fine. Each order in this database can have multiple shipments. If you ever bought from Amazon, you know how this works. They also work as a marketplace, so the products can come from different companies with different datas, with different dates, and also different delivery dates. Let's check another one. When will my package arrive? I'm not mentioning anything here, but it's getting the estimated delivery from the shipments table, joined with orders. And if you see, there is also the customer ID there. So this is a restriction that we put to the generation of the queries to make sure you are not querying data from anybody else. So this doesn't come from the NLP and Text-to-SQL. This comes from a restriction that we created for our system. All right, this looks okay. But let's try to query this one. So what items are in my most recent order? In this one, I didn't get an answer, so no SQL queries returned. We know from experience with LLMs, this could also generate hallucination. So this is also another restriction that we put here. We are not allowing it to give a response if they can't find the response from the data that we are providing. So although this data is there, it was unable to find. And my last test before I continue the presentation, what is the tracking number of my latest order? And here we also have a response query. Basically, it's going to the orders table and from the shipments table to get the tracking number, which is correct. So everything looks fine so far. Let's go back to the presentation and try to see what was going on here. Just in a safe scenario, I put a few slides with the example. But yeah, all right. So what AI solution do you guys think I used in this demo? So is it LLM with fine-tuning, LLM with RAG, LLM with AI agents? None of this. Think a little bit, what do you think this simple example is using behind the scenes? So actually, it's not using any of this. This was created as a very simple thing that it's based on a system that I created 20 years ago. So it uses a Prolog engine. It's the green part in the middle. We have a front-end container with simple HTML and JavaScript, an Nginx proxy that goes to the backend API container, which has a very simple Flask API script. And this processes the natural language query and sends to the Prolog engine. And all the grammar for the NLP and the text-to-SQL are scripts inside this Prolog engine. This will generate the SQL that we want, and later we'll go to this Postgres database and return the data to the user. So basically a very simple thing, very performatic, that exists for at least 40 years. You can do this kind of systems for a long time, but if you look today, you would think that some kind of LLM was used. So this was a book that was published in 1986, and it was already talking about this kind of systems. The solution that I mentioned was created much later than that, around 2004, so 20 years after the book. Before I continue to the actual LLM and RAG examples and AI agents, just a quick alignment on the concepts. So when I talk about large language models, I want you to remember that I'm talking about neural networks. So they were trained on very large data sets, and they produce statistical responses. So basically, everything that you can train will produce this with a likelihood that the response is there or not, and this can cause hallucinations or not. If there are much data about that, probably to get a right answer. If there is not much data about a topic on the training data set, it probably won't find the data. Just an example of size of LLMs, because one of the important things on your LLM is the number of parameters that it has inside it. So Llama 3.3 has 70 billion parameters and 43 gigabytes on disk. And DeepSeek R1 has 10 times the number of parameters and also 10 times the number of space on disk. But they use different techniques to train, and they use both similar training data sets. So that's interesting. Because of the different techniques, DeepSeek uses this stealing, and it generates a better result out of it. And how about RAG? RAG, when I talk about RAG, I'm talking about augmenting the prompts that will be used on your LLM. For instance, usual RAG flow, you will get the user question, Before you go to the LLM, you will transform that in vector embeddings. Then you will query your RAG database to get similar text. You do a similarity search in your vector database, where you get several text segments. You will use your original user question, user query, to produce an enhanced prompt, an augmented prompt with these text segments. And then we will query the LLM with the augmented prompt. Just an example, if you look here, we have the user question answering using the following information, and you put the text segments there. One important thing is that you want your vector store, when you query with your vector embedding, okay? When you use your vector embedding that was originated from the user query, you want to have a few text segments. You don't want a lot of response, because the output from the LLM will get confused and will produce worse results. So you want your vector store to be more precise and accurate when producing the text segments. So the fewer text segments the vector store produces, the better results you probably get from the LLM. And last, an AI agent. It always reminds me a little bit about robotics. We are talking about reasoning, planning, and action. So the difference from the original robotics algorithms that we usually know, if you know anything about robotics, is that they were more deterministic. They could learn, but they were more deterministic. Here, we have a certain level of autonomy to make decisions. So this is based on the way LLM works with that statistical data. So we have a level of uncertainty, and we don't have deterministic answers most of the time. So if you produce the same query, if you execute the same query over and over and over with LLM, RAG, and AI agents, you will probably get slightly different responses over time, and sometimes wrong answers. All right, so now I showed you the example from the Prolog engine, and I will use a similar version using LLM and RAG. Unfortunately, I'm not running the demo here because this laptop doesn't support it, but I will show you all the step-by-step of this RAG application. So the AI application would work in this way. You will get the user query in natural language as an input. As I said, you will process it to get your embeddings. So basically, you transform the user query into vectors, and then you will retrieve these text segments by similarity search from the vector store. That's the RAG part. Then you go to the LLM, and you use this augmented prompt like I showed you. You combine the user query with the resulting text segments, and you will ask them to create your response queries out of it. So this is the text-to-SQL part. And later, we will use an AI agent to get these responses, which can be multiple queries, even wrong queries. It will probably won't have that customer ID restriction that I showed, and the AI agent will fix all of that and go to the database. Once it retrieves the data from the logistics database, it will go again to the LLM to produce the final response in natural language. So let's see an example. Here we have, when will my package arrive? This query will become those vectors I mentioned. These will be the embeddings. And we will retrieve it from, in this case, I actually created the example, so I was using QDB, which is a very small and easy to use vector store for this. So we are going to retrieve the text segments out of this vector store. Then comes the context building part, and I'm going to combine the query and all the domain knowledge for the LLM. So this is a preparation part. And it will generate the queries that I want out of the LLM. That's the text-to-SQL part. This part, as I mentioned, it's not represented here, but this query will be transformed by an AI agent and will be processed on our Postgres database. And then I will have the results. And out of these results, I will get the natural language response and generate our user-friendly response. So that would be something like, when will my package arrive? All of this will happen with LLM, RAG, and AI agents. And I will get an answer like, your package from order number 4 is in transit via DHL and expected on January 25th. All this data comes from the database, and it could manage to get it out of the Postgres using AI. And how about multiple vector stores? So similar to one RAG solution, we could have multiple steps similar to this. So we could use that same combination of vector embedding, go to the LLM, use AI agents, get this block, and repeat for something else. So you could combine all these steps and go in cycles using different vector stores. The question is, why would you want to use multiple vector stores? For once, if you have different parts that you use in your application, different steps, you could use one single vector store. So you can put all this data, different parts, and iterate over the same vector store. That is simpler. But why would you want multiple vector store? Usually by testing this. If you are going to do any kind of LLM, you need to test multiple solutions. LLM, simple LLM, LLM with RAG, LLM with fine-tuning, LLM with multiple steps. And you need to test all of this because different scenarios, different training data, and different RAG ingestions will produce different results. So some will be better for your use case, some will be worse. In this case, I'm assuming that we have a scenario where it was worse if you use one vector store. So you could have like similar text from these different domains, and they were getting mixed up when you produce the text segments. So you want to make sure they are separate. When you query from the first step, you don't get data from the other domain. The example that I ran before, as I mentioned, it uses Qdrant as a vector store, and it's also using TinyLlama. That is a very simple thing to start testing. So you can run this on most notebooks, not this one, but anything a little bit better, you can run this example. And I'm also using LangChain4j, which despite the name, is not an exact copy or transformation from LangChain in Python. And I also have here a very interesting link from one of the creators of LangChain4j. So this is a demo that is interesting to see many ways of working with this. So just to exemplify how would it look like the multiple vector stores, as I said, it would be like an iteration, right? So you start with the input, the first embedding, and then you go to the first vector store with RAG1. You query the LLM, and then you start the process not by user input, but with an AI agent. The AI agent will get this response, go again to another vector store, which will be a RAG2, and then go to the LLM. And then here we would repeat this process. Let's imagine we have a third domain that we want to query. We would go to another AI agent that would get this last output and go to RAG number 3, and so on and so on. But as I said, you only want to do this if you tested before with one vector store, all these domains ingested on the same vector store, and you weren't satisfied with the results. Now you want to separate them to make sure your responses are not getting mixed up. Or for instance, maybe they are not getting mixed up, but they are getting too much text segments. as I said, this is also something worse for the LLM. You want short number of text segments. But I was talking now about increasing the number of vector stores. Now I'm going to talk about something completely different. Why not remove all vector stores? So one thing that happens is if you don't have a very large number of data, so your data is limited, you don't want to use a vector store as well. The LLM machines today, if you go to Anthropic or Gemini or whatever you're going to use, imagine a very large model that we have already today, it allows you to use a very large input as a prompt. So you could simply use techniques like system prompts, which is an inversion on the reg idea. So instead of having the user query enhanced, augmented by text segments from your private data, from your vector store, you are going to start with a fixed system prompt or with a system prompt that can slightly vary depending on the user input. So you could have an AI agent to select this system prompt. I will show you an example of how this works. So you would start with this system prompt, which is predefined, and then you would enhance the system prompt with the user question. Just the database again, so we can remember, because I will show some examples. So on the orders database, I have the status for the whole order. On the shipments, I have the tracking number and the status for each of these orders. And on the tracking event, I have a timestamp and the location for these events. So let's imagine this is my system prompt. You are a helpful assistant that classifies user requests. There are 4 sectors in our department. I'm using here sectors instead of tables, but they represent the tables. Orders, shipments, products, and tracking events. I want you to respond with a specific sector name based on the user support query. And then I would enhance this with the support query, with the user query. So here, of course, you are seeing I'm just putting the table names. So we will see that we will get some responses wrong, but it will be right most of the time. And as I said, if you use a modern LLM, I was using a tiny llama, so it doesn't allow you very large prompts, but you could put the entire entity relationship model in my system prompt. So it would know all the data types, it would know all the fields for each of these tables. I will use the same queries that I used before. So what's the status of my latest order? And the response was orders. So it got correct. So that was a simple one. There is order on the query. Maybe it just gets out of it. When will my package arrive? This looks like a more tricky one. So it answered me with tracking events. I put this as a yellow, so not fully right, because the correct answer would be from shipments. But as I said, it didn't have enough information, and you can also extract this information out of tracking events. It's just not the best approach. But I only put the table names, so it was a good guess. So it's using the LLM, the statistical data. It probably was trained on some sort of logistics information, logistics data, so it can understand a little bit that, okay, the package arriving should be related to tracking events. So it's not wrong, but it wouldn't be the best query to execute. The next example, show me all my shipments that are currently in transit. And that was another easy one. It has shipments on the query. It got the answer right. And show me my last 3 orders. Same thing, I'm talking about orders. It's saying that it's classified as orders. And what is the tracking number of my latest order? And this got a bit tricky. Although there is tracking on the name, it also has order on the query. So it tried to answer as orders, but it couldn't find out where is my tracking number. So my tracking number is per shipment, because I can have multiple shipments for one order, just like Amazon does. So one order can produce multiple shipments. That's why the tracking number is there. But it tried to guess on the orders table, and didn't got it right. All right, so what can we understand about this? Basically, my idea here is to show you that before you can decide on which tools you need, is it LLM? Do I need a vector store? Do I need to build an AI agent? Which agent framework do I need? The first thing I showed you was, when I started the demo, was a brief architecture, a very high-level architecture of my application. So that's the idea. You need to have this idea of what you want to build before you can select the tools. So even with an old, 20 years old Prolog system, I could produce similar results to what the LLM is capable of generating today. Of course, I have more power today. I can actually generate very complex natural language response that was not possible with Prolog, or at least very, very much difficult. But I could do something about it and have simple responses as well. So that's the idea here. Think about your systems before you select the tools. Of course, everybody wants to test LLMs, test AI agent frameworks, but you need to have an idea of the product before you build your system. So design what you're trying to achieve, and then you can start testing different tools. Once you have these different tools, you can do this, sorry, you can do this with a better and more effective way. And just before I finish, I also put here on the slides a few workshops. This is more for people that work with Java, but they are very simple to follow. So we have 2 workshops, both by the Quarkus team and the LangChain4j team. So one by Julien Dubois, which was the example I showed first, and also interesting books, one about LangChain4j, and one about applied machine learning and AI, which is this image we have here. And the last one is about that Prolog book that I showed earlier. And that's it for me. If you want to get in touch, this Scan Me QR code is my LinkedIn profile. Feel free to reach out, or feel free to reach out during the event as well. Thank you.